Alrighty, howdy folks. Let's continue with the section 1.1, that is chapter 1, section 1. Let me, nope, I don't want to pause it. Minimize it. Okay, good, let's go. Sorry about that. So let's look at problem 14 from that and verify whether the given function is a solution of the given differential equation. So there's a question like this: y prime plus 20y equals 24, y equals 6/5. Verify whether y equals 6/5 minus f raised to negative 26. That stuff. Is that the solution of the differential equation y prime plus 20y equals 24? So before I actually show you how to go about doing this, let me give a bit of motivation. If I said x plus 2 equals 5 and asked you, is that an equation? You would say, yep, it is, right? We talked about it. What kind of an equation? An algebraic equation. Typically, when you're given an equation like that, what do? You would say you would solve for x, right? X plus 2 equals 5. And so you subtract the 2 from both sides and you say x equals 3. Now, I could state the question in a slightly different way. I could say, is x equals 7 a solution of x plus 2 equals 5? Are you with me? Is x equals 7 a solution of x plus 2 equals 5? I know, obviously, no, it's not. How did you know that? The way you knew that is, you picked the left-hand side, which is x plus 2. And now I'm saying, is x equals 7 a solution? So you plug in 7 for x. So the left-hand side becomes 7 plus 2, which is 9. Now you look at the right-hand side. On the right-hand side, I had 5. I said x plus 2 equals 5, right? So the right-hand side was 5. And you go, wait a minute. When I plug 7 for x on the left-hand side, I get 9, which is not equal to 5 on the right-hand side. So you will say, nope, that's not a solution. X equals 7 is not a solution of x plus 2 equals 5. Right? So the whole idea is that you plug whatever the claimed solution is and verify whether the left-hand side equals the right-hand side. Right? And now, one more example quickly. Is x square for x square minus 1 equals 0. X square minus 1 equals 0. Is negative 1 a solution? Okay, you say, hang on, give me just a second. Left-hand side is x square minus 1. Let me plug negative 1 for x. So negative 1, the quantity square is 1. 1 minus 1 is 0. Yeah, the left-hand side is equal to right-hand side. So you'll say, yep, negative 1 is a solution of x square minus 1 equals 0. The reason I brought that up is, it is precisely the same way it works even for differential equations. What do I mean? Plug this value of y and check whether the left-hand side equals the right-hand side or not. The thing is, plugging is not a straightforward thing like it was in the case of x square minus 1. You may need to do some preparatory work. As in what? Here we are given y equals 6/5 minus 6. But we need a y prime. So we actually need to find the derivative of y and take the derivative and plug for y prime. Right? And for y that you see here, we can plug 6/5 minus this stuff. Okay, that's exactly the process. So we'll say for all such problems, the idea is to show that left-hand side equals right-hand side. Y is equal to this. That means y prime. Let's differentiate. The first term, 6/5. What's the derivative of 6/5? 0, because the derivative of a constant is 0, minus we need to take the derivative of 6/5 e to the negative 2x. So I see that minus here. A constant multiple can be yanked outside. So 6/5 times the derivative of e to the negative 20x. Chain rule. The derivative of e to the x is e to the x. So the derivative of e to the something else is e to that something else times the derivative of that something else itself. Right? That's how chain rule works. The derivative of e to the negative 20x is e to the negative 20x times the derivative of negative 20x, which happens to be negative 20. Okay? Now, if I simplify this, I get 24e to the negative 20x. Right? Okay, so now let's plug. Now we are ready to figure out what the left-hand side is. Left-hand side is equal to y prime plus 20y. For y prime, let's plug this 24e to the negative 20x, and for y, we plug that. And trust me, simplify this, multiply, and all that stuff, distribute, and then it turns out that 24e to the negative 20x minus that goes to 0, and so you're left with 24. And is that equal to the right hand side? Yep, it is. So it turns out that left hand side is equal to right hand side here. So we will say the given function is a solution of the differential equation. Does that make sense? Now, just about every other problem in this section, we are going to do the same thing. Finding the derivative may not be so straightforward, but the whole idea would be to just verify whether the left-hand side is equal to right-hand side. Cool? All right, let's move on and solve a few more problems. Problem 16. dy dx equals square root of y over x. That's the differential equation. And the claim is y equals square root of x plus c1 the quantity square. Is that with x greater than 0 and c1 greater than 0, is that the solution? Right? As before, we need to figure out what dy dx is given y equals square root of x plus c1 the quantity square. And we say, wait, so how do we differentiate this? We need to do chain rule. D dx, by the way, of square root of x. That's one of those things I ask my students. If you were taking any class from me, either Calculus 1 or Calculus 2, I would just ask you to memorize d dx of square root of x because it shows up in so many places. So d dx of square root of x is 1 over the quantity 2 times square root of x. Cool? So keep that in mind. Now, how do we do this? We could FOIL this out and then differentiate. That's one possibility. Or we could apply chain rule. Y prime is 2 times this whole quantity times the derivative of square root of x plus c1. But the derivative of c1 is 0 because the derivative of a constant is 0. And like I said, derivative of square root of x is 1 over 2 square root of x. That's what I did. Cool? Now, 2 and 2 cancel each other out. And we are left with square root of x plus c1 over square root of x. Right? Cool. What did we do? We found y prime. So what's the left-hand side? Left-hand side is dy dx. Hey, wait a minute. I was like, what did I do? Okay, this is what looks like I did. I picked the right-hand side square root of y over x and asked myself, hey, can I write that in a different way? The thing is, we know what y ought to be. Y is square root of x plus c1 the quantity square, and So I substituted that quantity for y. And so we have this. Now you tell me, pay attention please. Is square root of a over b equal to square root of a over square root of b? Are you with me? Square root of the quantity a over b, is that square root of a over square root of b? Yeah, it is. Right? So we have square root of the top, square root of some quantity square. What is square root of some quantity square equal to? Like, what is square root of x square? That's equal to x, man. Let's see. So let me digress and ask you a few questions. What is square root of 4? Oh, come on, man. I'm in differential equations. Why are you asking me a stupid question like that? Yeah. Please, indulge me. What is square root of 4? That's easy, man. That's plus or minus 2. Uh-oh. What's with that? That's big tam not equal to. Right? So if you said square root of 4 is plus or minus 2, then all I want to say is that's big tam not equal to 2, plus or minus 2. Now, next. What's square root of x square? I think that's plus or minus x. Nope, that's big tam not equal to plus or minus x. Okay, one more try. What's square root of x square? No, I got it this time, man. Square root of x squared. No, what was I thinking? Square root of x squared is just x. Right? Square root of x squared is just x. Dang. That's not equal to just x. Okay? If x squared is equal to 4, then what is x equal to? Now you're like, dude, please, I'm really tired of this. Looks like I'm so stupid I don't even know what it is. So I'm not gonna answer that question. I'll ask you to tell me what the answer is. Is that what you're saying? Don't worry about it, man. I was in the same place not too long ago. Okay? When my teacher asked me these things, I was like, yo, what? Yeah. Here the answer is x equals plus or minus 2. Oh, dang. That is true. If x squared equals 4, then x equals plus or minus 2. Now check this out. The last problem, you can arrive at the answer by doing something totally wrong. You can apply a wrong method and still think, yep, everything I did is just fine and dandy. No, it ain't fine and dandy. Check this out. If I have x squared equals 4, in the next step can I say, well, take square root on both sides? Yeah, that's okay. And now, is square root of x squared equal to x? Yup. Is square root of 4 equal to plus or minus 2? Yup. Ta-da! That implies x equals plus or minus 2, man. That's why I was telling you, right? When you said what square root of x squared, didn't I say x? And when you asked me what is square root of 4, didn't I say plus or minus 2? Now look at this. That's perfect. Nah, it's not. It just so happens that we made two mistakes that perfectly canceled each other out, giving us a false sense of confidence that, yep, we must be right. The thing is, no, square root of x squared is not equal to x, nor is square root of 4 equal to plus or minus 2. Oh, really? Okay. Now, what's the right answer? The right answer to square root of x square equals, anybody? The right answer. Not x, not plus or minus x. You said absolute value of x, then please pat yourself on the back. If I had been there, I would have done that, but maybe not with this situation. Yep, square root of x squared is actually absolute value of x. What's the big deal about that? The big deal about that is, now if I ask you what is square root of 4, you can look at 4 as 2 square. So square root of 2 square is what? Absolute value of 2. But absolute value of 2 equals 2. So what is our eventual result for square root of 4? Boys and girls, square root of 4 is just equal to 2. It is not equal to plus or minus 2 or anything like that. Square root of x square is absolute value of x. Square root of 4 is just 2. Cool? Now let's apply that. Apply the correct method, and you see x square equals 4. Take square root on both sides. Cool. Square root of x square is absolute value of x. Square root of 4 is just 2. Now the question comes. If absolute value of x equals 2, what can you say about x itself? That's nothing but x equals plus or minus 2. How'd you get that, man? Well, can I really claim that if absolute value of x equals 2, then automatically x must be plus or minus 2? Yeah, because let's pick that plus 2. Could that be an answer to this equation? Yeah, absolute value of positive 2. What's absolute value of positive 2? 2. Okay, so that means x equals positive 2 is definitely a solution of this equation. What about x equals negative 2? Okay, plug negative 2. The left-hand side is absolute value of negative 2, which is 2. And sure enough, that is equal to right-hand side 2. Right? So x equals either positive 2 or negative 2 if absolute value of x is equal to 2. Right? That's the idea. Okay, why was I talking about this? What's this got to do with the problem that we were doing? It's got everything to do with the problem that we were doing. Now tell me, what is square root of x plus c1, the quantity square? What is that equal to? Be correct. Maybe I should have joked and said, be absolutely correct. Is absolute value of square root of x plus c sub 1. Right? Over square root of x. What did I first do? I said this is square root of a over b, square root of a over square root of b. And for the top, square root of this square thing is absolute value of that thing. Right? And that's equal to square root of x plus c1 over square root of x. What happened to the absolute value sign, man? Right? Yeah, I just took it out. I don't like absolute values. Nah, I'm just kidding. You cannot do that. You cannot simply remove absolute value. I hate absolute values. I'll just take it out. It's not like a simple bracket or a parenthesis that, if it's okay, you just remove it. You gotta be careful. But there is a good, valid reason why I could remove the absolute value sign. If you need to, pause the video and ask yourself, why is that? What legal grounds did this guy pull that absolute value sign out? Okay, here is the idea. Remember that the absolute value of a positive quantity is the quantity itself. But the absolute value of a positive quantity is the quantity itself. So let's ask, is this square root of x plus c sub 1? Are we guaranteed that that is going to be?
Your question.
Alexa, stop. Alexa, stop. Is square root of x a positive quantity? Rather, in fact, is square root of x plus c1 a positive quantity? Well, let's look at it this way. Are we given that x is greater than 0? Let's say something like a 4. Is square root of 4 guaranteed to be a positive quantity? Yeah. Is square root of 1 a positive quantity? Yeah, 1. Square root of 1 is positive 1. Not plus or minus 1, just 1. Right? So square root of x is guaranteed to be positive, and we are also given that c1 is positive. So we got a positive quantity plus another positive quantity. Is there any way that could actually turn out to be negative? No, it cannot. It has to be positive. And because of that, we can remove the absolute value sign around square root of x plus c1 in this context. Right? Yeah. That's why I love this problem. There are so many things that we kind of take for granted, especially as engineers. Dang, we don't think this deeply at all about, yeah, some stupid absolute value sign, man. Ah, no, 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 no. Right? Cool. Let's move on. So, by the way, LHS is equal to RHS, right? So y prime was the left-hand side, dy dx or y prime, and that turned out to be this, and this turned out to be the right-hand side. Also, when simplified, turned out to be what left-hand side simplifies to. So we're done with that guy. Now, 2xy dx plus x squared to y, and apparently we need to do x squared y plus y squared equals c1. Is that a solution of the differential equation? Whoa, wait a minute. Is the left-hand side a differential equation to begin with? Recall, could you have a differential equation that contains differentials? Yeah, so this happens to be a differential equation containing differentials. Okay, but wait a minute. Up until now, did we have the solution to be y equals some function of x? Huh? But now we have something like x squared y plus y squared equals c1. And we are being asked, is that a solution? That's a weird looking solution. Not really. This is what is called an implicit solution. Right? You don't have y as a function of x explicitly expressed that way. Y equals some function of x. If you had that solution to be that way, you would call it as an explicit function. Y is explicitly expressed as a function of x, you would say. But this is a situation where y is an implicit function of x. In a sense, you cannot right away tell that y is a function of x, but if you manipulate, if you could manipulate, it turns out y could be written as a function of x. Now, in cases like this, we need to do what's called implicit differentiation that we learned in Cal 1. Okay, so let me go over that stuff. Let me first digress and talk about how this thing works. What is this implicit differentiation? How does it work and all that? Is d dx the derivative of x squared? What is that equal to? You'll all say, that's 2x, man. Yes, you're right. What's d dy of, what is d dy of y squared? Yeah, similar thing, 2y. Cool. Now if I asked you, what is ddx of y square? What? That's gotta be 0, man, because y square is a constant. No, y could be a function of x, so y square is a function of x. I'm not telling you precisely what it is of how y and x are related, but just take it that y is a function of x, some kind of a function of x. Right? Guess what? This is actually what chain rule was all about. What is ddx of y square? The way you compute that is, you first figure out the dy of y square and multiply by dy dx. Cool? ddx of y square is dy of y square times dy dx. Okay, now what is dy of y square? 2y. So this becomes 2y dy dx, or dy dx can be written as y prime. Alright, so you really need to know this kind of a chain rule if you want to do implicit differentiation. Alright, so with that in mind, what are we doing? We are taking the derivative of the left hand side of this solution, purported solution, and setting that equal to the derivative of the right hand side. If left equals right, then the derivative of the left must equal the derivative of the right. Here we are assuming differentiability and all that stuff. Okay? So let's embark on that. Can you differentiate the left hand side? Can you tell me what the derivative of the first term, x squared y, is? What is ddx of x squared y? Wait a minute. Y is a function of x. So you have x squared, which is some function of x, and y is also some other function of x. So how do you differentiate that? Product rule, because they're multiplying, right? And how does the product rule go? First function times the derivative of the second function plus second function times the derivative of the first function. So x squared, first function, times the derivative of y with respect to x. That's just y prime. Plus the second function y times the derivative of the first function, which is x squared, and derivative of x squared with respect to x is 2x. So y times 2x. Plus, there's a plus here, so I put a plus here. What's ddx of y squared? We just discussed. That would be 2y y prime. And that's equal to, what's the derivative of c1? c1 is a constant. That is 0. So we have this. Okay, man, so what? Our objective is, after we do an implicit, our objective with this implicit differentiation is, after we do this thing, we want to figure out what y prime is. Can we figure out y prime from what we got here? Yeah, simple algebra. So solve for y prime. For that, factor out a y prime from the first and the third terms. You get this, and subtract a 2xy from both sides, and so that you have y prime stuff on the left hand side and the terms that do not have a y prime on the right hand side, and now divide both sides by x squared plus 2y, and you get y prime to be negative 2xy over x squared plus 2y. Cool. All right. Now, if you look at the differential equation itself and figure out what dy dx is, that is, divide both sides by dx and subtract 2xy and divide all of this, just manipulation. If you do that, the differential equation itself can be rewritten as dy dx equals negative 2xy plus this thing. And sure enough, dy dx, if you plug this, left hand side is equal to right hand side, right? Wonderful problem. And in a quiz, in a test, I am very likely to ask you a question on implicit differentiation, because I think it's a wonderful application of the stuff that we learned in Calculus 1. All right. Next, find y prime. Ooh. So I could, because I want to test whether or not you could do implicit differentiation, I probably would ask a question like this. You may not see something like this in the textbook. So, but I like this. I'm going to ask questions like this. Okay. So how do we do this? Well, let's ooh, 3 stars. This is a 3-star problem. What that means is that problem or a problem just like that is almost a guarantee to show up in a quiz or test. Okay. Differentiating both sides with respect to x, we get, oh, wow. Is that really true? Maybe I went a little too fast. What do you think? Is the derivative of the first term, sine of x squared y cubed, what I wrote? The answer is yes. Cosine sine of something, the derivative is cosine of that something, times the derivative of that something itself, the argument of something. So now when we look at x squared y cubed, we are supposed to figure out ddx of x squared y cubed. Are you with me? Sine of something, derivative with respect to x is cosine of that something, times the derivative of that something itself. That means the stuff inside the parentheses. Now focus on the stuff inside the parentheses, derivative of that. ddx of x squared y cubed is, we need to apply product rule. X squared, the first term, times the derivative of the second term y cubed with respect to x is 3y squared times y prime. Okay, plus the second function y cubed, that's what I wrote here, times the first derivative of the first function x squared derivative is 2x. So that's why you see a 2x y cubed times 2x or 2x times y cubed. Right? So we took care of the derivative of the first term. Now tell me, what's the derivative of x over y? That is not so simple as it looks, because both x and y are functions of x. So would you agree that we need to apply quotient rule? What's quotient rule? Low d high minus high d low over low low. That means the low is the denominator times d high is the derivative of the high, that is the numerator, minus high d low minus the numerator times the derivative of the denominator over low low, that means square of the denominator. Low times low, denominator times denominator. Cool? So let's apply that. Y, well, low is y, times d high, the derivative of x is 1. So y times 1. Ah, dang. That's not what I did. I could have done that, what I said, the quotient rule, but look at what I did here. Well, what I did is, I looked at this x over y as x times 1 over y and applied product rule. Can you do that? Yeah, of course you can. So x times 1 over y, first function is x, that's what I have, And the derivative of 1 over y is negative 1 over y square times y prime. When the derivative, let me say it again. The derivative of 1 over y with respect to x is negative 1 over y square times y prime plus 1 over y, which is the second function, times the derivative of the first function x, which is 1. So that's why you see plus 1 over y. That's another way. If you wanted to do the quotient rule, yeah, that's perfectly fine too, right? You will get the exact same thing after you simplify it. If you need to pause the video and take a look at exactly how I got the derivative, please do that. You must grasp this. Okay? Cool. Now let's look at the right-hand side. Secant of xy. What's the derivative of secant of xy with respect to x? Secant of something. The derivative of secant of something. Oh, that's nothing but secant of that something, tangent of something, times the derivative of the something itself. Right? Why is that? What is d dx of secant x? Secant x tangent x. So based on that, I'm saying secant of something is secant of something, tangent of something, times the derivative of that something itself. And that's why I have secant of xy, tangent of xy, times the derivative of xy itself, for which I applied the product rule and said xy prime plus y. Right? First function times the derivative of second function plus second function times the derivative of x, which is 1, so y times 1. Plus sine inverse of x. Sine inverse of x is 1 over square root of 1 minus x squared. Now, this is a good time to tell you really have to have all the derivatives memorized. It's absolutely essential that you do. Okay? So, here, what's the derivative of sine inverse of x? You should know. It is 1 over square root of 1 minus x squared. You should know that especially because quite likely that pretty soon you would be actually solving a differential equation and you will get integral of 1 over square root of 1 minus x squared. If you know that the derivative of sine inverse x is 1 over square root of 1 minus x squared, then you know that the integral of 1 over 1 minus square root of 1 minus x squared dx is sine inverse x. So you got to know this. Okay? All right. Now, wait a minute. All this big stuff. What are we supposed to do? We're supposed to figure out what y prime is. How do we go about doing it? Multiply everything out, that is, distribute out. This times this first term inside the square bracket, the cosine thing times the second term, and like that. Distribute. And pick up all the terms that have a y prime and put them on one side by subtracting from the right hand side. If you see some term with a y prime in it on the right hand side, if you see a term or terms with a y prime on the right hand side, subtract those terms from both sides so that it disappears from the right hand side. It should show up only on the left hand side. Similarly, on the left hand side, if you see any terms that do not have a y prime, subtract them from both sides so that they disappear from the left hand side. That's what I did. So if I multiply, looks like I was a bit patient. So if I multiply this, then we get 3x squared y squared cosine of x y and plus 2xy cubed. Man, I can't imagine I had that kind of patience. That's equal to multiply all of this. Yup, and the next step looks like I got all the y prime terms on one side, right? And I factored out a y prime. And all the terms that do not have a y prime, I have them on the right hand side, and this is what I have. And the beauty is, uh, now I can divide both sides by whatever y prime is multiplying, and we end up with that simple looking expression. Cool? Folks, very, very, very likely to ask you this kind of a question. Here I have sine of x square y cube. I could have something like e to the x cube y to the 4 plus x square over y square, you know, secant of x square y or cotangent of x square y cube or cotangent of x cube plus y cube. All kinds of things I could have. Okay. If you need any practice, maybe you could grab somebody's calculus book and look at the section on implicit differentiation. But here is the idea. Cool? All right. Oh, this is a good problem. Y equals 2xy prime plus y prime square. We need to verify whether y square is equal to this is a solution or not. Cool. How do we go about doing this? Our objective is to figure out y prime. Can we figure out y prime for this one? How do we start? Well, simply say differentiate both sides with respect to x. Right? So differentiate both sides with respect to x. So we say when we do that, the left hand side is 2y prime and the right hand side is what? Yeah, because notice c1 is a constant. So c1 times the constant multiple can be yanked out times the derivative of the stuff inside the square inside the parenthesis, and which is the derivative of the first term is x is 1 and the derivative of the constant is 0. So c1 times 1 plus 0 or c1 times 1 or c1. That's what I have. As simple as that. Okay, allow it to sink in. Please pay attention. And then our objective is to find y prime. Are we in a position to doing that? Yeah, divide both sides by 2y and you get y prime equals c1 over 2y. Cool. Now, so we took the solution and figured out what y prime is from that one. Now, somehow we need to substitute this into the differential equation and show that the left hand side equals right hand side. That's what we need to do. Let's see if that task is simple or not. For this, you got to be clever sometimes. The right hand side is what I picked. Right hand side is 2xy prime plus y times the quantity y prime squared. Cool. Now, can we plug the y prime that we got from the solution when we differentiated the solution? Yeah, you get 2x times, instead of y prime, I'm plugging c1 over 2y. Again, instead of y prime square, I'm plugging c1 over 2y, the quantity square. And we can do cancel and we can simplify that and write like this. Let's pause for a second. Oftentimes it's a wonderful thing to pause like that and ask, what the heck are we doing? What are we trying to show? So what are we trying to show here? We're trying to show that the right hand side equals the left hand side. Yeah. Now I got it, man. Yep. This is what we have for right hand side. Does that look anything like the left hand side, which is just y? Boggles the mind, doesn't it? Okay, come on, man. This x times c1 over y plus c1 square over 4y doesn't look anything like just a simple y. You're telling me that? Yes, I am. How? I'll check this out. Notice what y square is equal to. Y square is equal to c1x plus 1/4 c1 square. Would you agree if I multiply this out, distribute it out? Y square is c1x plus 1/4 c1 square. C1x plus 1/4 c1 square. Hey, if I factor out a 1 over y from this, in fact, factor out a 1 over y c1, then we get 1 over y c1 times x plus 1/4 c1. Hey, that c1 times x plus 1/4 c1, that's nothing but y square. So this is 1 over y times y square. And what is that equal to? That's equal to y. That's equal to left hand side. Right? Beautiful problem. Very nice problem. You got to appreciate, the kind of manipulation that you need to think, that you need to make, for which you need to think. Cool. All right. And what else? Problem 22. This is a good one. Boy, you gotta really pay attention to this one, huh? There's so many things I need to clarify for you. Let's see. That's why I have a digression. Let what? Oh, cool. In America, you can be guaranteed. You ask any high school student, hey, what is absolute value of 2? That's equal to 2, man. They will all say it, and they get it right. Absolute value of 2 equals 2. And they also know this. What's absolute value of negative 2? And they'll say that's equal to 2. And they're right. And now if you say, oh, why is the absolute value of negative 2 equal to 2? And they give the triumphant smile and say, ah, that's because, that's the distance on the number line from 0. And since distance cannot be negative, the distance from 0 to negative 2 is just positive 2. So that's why absolute value of negative 2 equals 2. And I feel like going and patting their back and saying, yep, you are right. It's because of the distance from 0 on the absolute on the number line. Okay, son, tell me this. If x is less than or equal to 2, then what is absolute value of x minus 5 equal to? What? That's like on real number line, the distance from, yeah. I don't know, man. Yeah, I know, right? So that distance from zero thing is there's nothing wrong with it, but turns out to be fairly inadequate at a college level. So let's do the college thing. What's the definition of absolute value of x? Absolute value of x is x if x is greater than or equal to 0, negative x if x is less than 0. Cool? Now, okay, what's the big deal about this stupid thing? Let's ask ourselves this question. Use this definition and tell me why is the absolute value of 2 equal to 2. Okay? Similarly, use the definition and tell me why is the absolute value of negative 2 equals positive 2. You must use the definition, not this number line thing and all that. For that, let me help you. I'm going to read the definition once again, but this time wherever I see an x, I will say quantity. Okay? Absolute value of a quantity equals quantity if the quantity is greater than or equal to 0. Equals negative of the quantity if the quantity is less than 0. Cool? All I did is simply, wherever I saw x, I said quantity. If I saw negative x, I said negative of the quantity. That, I think, helps in answering the question. What is absolute value of 2? The moment I say, what is the quantity in my case? Oh, the quantity is 2. Cool. What is the absolute value of a quantity? It depends. Depends on what? Whether that quantity is greater than or equal to 0 or less than 0. So is 2 greater than or equal to 0 or less than 0? Clearly is greater than 0. So we should take the top path. So what does this say? Absolute value of a quantity in that case is equal to the quantity itself. So that means absolute value of 2 is just 2 itself. Cool? That's the idea. Now, if you go to absolute value of negative 2, now what is the quantity? The quantity is negative 2. What is the absolute value of the quantity equal to then? Well, we have to take the bottom path because the quantity negative 2 happens to be less than 0, it happens to be negative, we need to take the bottom path. And what does the bottom path say? This must be equal to negative of the quantity. That means negative of negative 2, which happens to be positive 2. I got to you. When somebody explained it this way to me, poof, I was like, dang, why didn't anybody teach me this way, man? And so I said, like, if I were to ever become a teacher, this is exactly how I would teach. So, whoever taught me, unfortunately, I don't remember who it is. Maybe I do. Maybe it was Ed Dixon. Ed Dixon, I think, was the one who showed me this. Okay, cool. So, how does that help us answer this question? What is absolute value of x minus 5? So the quantity now is x minus 5, right? Quantity is x minus 5. So what is the absolute value of the quantity equal to? Well, it depends on whether the quantity is positive or negative. What can we say about x minus 5? Is it positive or negative in this context? What do you mean by context, man? Yeah. What is the context? The context is apparently x is less than or equal to 2. Can we figure out whether x minus 5 is positive or negative if that's the case? Wait, x is taking on values of 2 or less than 2. When x is equal to 2, we have 2 minus 5 is negative 3. Oh, the quantity x minus 5 is negative. If we pick 1, Then 1 minus 5 is negative 4. Oh, 0, negative 5. Oh, that's also negative. So for every value of x less than or equal to 2, this quantity x minus 5 happens to be negative. Do you agree? Let me repeat that. For every value of x that is less than or equal to 2, x minus 5 is clearly negative. So absolute value of that quantity must be negative of that quantity, which makes it either negative x plus 5 or 5 minus x. Either way you can write. Absolutely essential that you understand this. Okay. One more digression, I suppose. Is y equals absolute value of x differentiable? I don't know about you, but when I was in calculus, I hated that question. What's this stupid differentiable, man? Just tell me to find the derivative, I'll find the derivative. But no, you really need to understand. That's why we are in a college in America. We are better than that. So let's ask, is y equals absolute value of x differentiable? For that, let's look at the graph of y equals absolute value of x. Is this function differentiable everywhere? Thing is, no, not at x equal to 0. Absolute value graph is not differentiable at x equal to 0. Right? Why, man? I don't want to do that. Why is absolute value of x not differentiable at x equal to 0? That's because, I'm sure some of you are going, that's because there's a sharp corner. Yes, you're right. But when there is a sharp corner, why is the function not differentiable at that point? Why? Right? What's the derivative? What is the derivative of a function at a point? Oh, it's the slope of the tangent drawn to the curve at that point. Slope of the tangent. Good. So if I want to say find the derivative at some point like here, not at 0, some other point, what should I do apparently? Oh, draw a tangent to that curve and look at what the slope of the tangent line is. That's it. You got the derivative. All right. So I want to draw a tangent. How do you draw a tangent? Tangent, man. You just look at it and you could draw. Just, are you kidding me? No, I'm not kidding you. The thing is, oh boy, I don't know. Not right from this one. The right way of drawing a tangent, in my opinion, is suppose you want to draw a tangent to the curve at that point. Please excuse my pathetic drawings right now. You need to pick a point to the right and draw a line passing through those 2 points. Is that the tangent? Oh no, that's not the tangent. That's actually the what? Anybody? That's the secant line. Oh yeah, that's the secant line. Cool. Now you pick another point even slightly closer and draw another line passing through the original point where you need to draw a tangent and this new point that you picked. Is that the tangent line? No, that's also the secant line. So you keep repeating this process each time, getting closer and closer to the original point, never ever reaching it, but keep getting closer and closer and keep drawing the secant lines. And then the limit of those secant lines is what the tangent line is. Oh, come on. No. I wouldn't be telling you, spending so much time on telling you about all of this if it's not important. It is really, really important. Okay, we got a stupid tangent. Okay, what's the slope of the tangent? Is the derivative. But no, not so fast. But you mean I gotta do something more? Yeah, you got to. That is, just as you picked points to the right and kept coming closer and closer, you need to do the same thing with points on the left. You pick a point to the left, draw a secant line, let it come closer, and draw another secant line, and keep coming. And the limit of those secant lines based on the points to the left, that is going to be the tangent line. Cool? What's the big deal about it? The big deal is when you have a curve like this, a nice and differentiable curve, then whether you use points to the right and draw a tangent line or use points to the left and draw a tangent line, it will both be the same. You would get the same tangent line. That's the key. Tangent based on points to the right or tangent based on points to the left would be exactly the same. Now, would that be true for absolute value function at x equal to 0? What's the tangent line based on points to the right? Well, that's going to be this line itself. That's the tangent based on points to the right drawn at x equal to 0. However, if you were to pick points to the left and draw the tangent, that tangent line would be this guy. Are the two tangent lines the same? They're not. So when I say what's the derivative? Well, find the slope of the tangent, man. Yeah, but which tangent line, man? Right? There are two different tangent lines. And that ambiguity is precisely why this function is not differentiable at x equal to 0. Y equals absolute value of x is not differentiable at x equal to 0 because the tangents based on points left and points right are not the same. In fact, any sharp corner, it's the same situation. Okay? So that is the idea. Cool? Now, here is another question. Is y equal to x times the absolute value of x differentiable? Whoa. What? Let's see. Okay. What exactly is this x times absolute value of x? How does that look? Right? As such, we have no idea what in the world is x times absolute value of x, man. But check this out. Use the definition. Definition of what? Definition of absolute value. Right? What is the definition of absolute value? Is equal to x if x is greater than or equal to 0, negative x if x is less than 0. Use that definition. What do you get? X times, can I say that? Yeah, because what I'm going to do is, if x is greater than or equal to 0, I'm going to replace the absolute value of x with a simple x. So what would I be left with? X times x. What is x times x? X squared. That's what you see there. On the other hand, when x is less than 0, what will I replace x absolute value of x with? Negative x. So what am I looking at? X times negative x. Isn't that equal to negative x squared? So basically, x times absolute value of x is just simply x square if x is greater than or equal to 0, negative x square if x is less than 0. Cool? Now we have some kind of an idea. I see. Let's ask one more thing. If we were to look at the graph of this, how would the graph of x times absolute value of x look like? Do we know the graph of just x squared? If I say, yeah, man, that's a simple parabola. Yes, you're right. You're absolutely right. What does the graph of negative x squared look like? I know all my American wonderful friends are so good at these graphs. Everybody knows. X squared is a parabola that opens up. What's the graph of negative x squared? That's a parabola that opens up down. It's a reflection of negative x squared is a reflection of x squared about the x-axis. Right? So what that means is the graph of x times that x squared and negative x squared thing looks like this. On the right half, you have on the right side of 0, on the positive half rather, you have a parabola that opens up. On the left hand side, you have a parabola that opens down. Right? This is how the graph looks like. Now the question, is this differential at x equal to 0 especially? Any thoughts? How should you even think about it? Can you simply say, well, if absolute value of x is not differentiable at 0, x times absolute value of x is also not differentiable, man? No. You cannot use that logic. What's the foolproof way? Draw a tangent at x equal to 0. How do you draw a tangent? Be sure to draw the tangent based on points to the right and points to the left. If you did, how does the tangent drawn based on points to the right look? At x equal to 0 would be a horizontal line. Similarly, tangent based on points to the left would also be a horizontal line. Same horizontal line. Okay, what's the slope of a horizontal line? 0. So 2 questions. Is x times absolute value of x differentiable at 0? Of course it is. What is the derivative? 0. Is the function differentiable everywhere? Yeah, it is. Now you might say, why did you talk about all this stupid differentiability, man? Why do I care? Oh, you do care. Because you're dealing with differential equations. Notice that equation to be y prime equals 2 times absolute value of y. If the question is y equal to x times absolute value of x a solution? If y is not even differentiable, how can you talk about y prime? If y is not differentiable, y prime does not exist. So how can you claim something that does not exist to be a solution to this problem? You see? So the minimum requirement for the solution is that the solution function better be differentiable everywhere in the domain. That's why we went through all of this. Cool? And so, this is now another interesting one. What's the derivative of this? Well, the derivative is on x greater than or equal to 0, 2x, and on this one, negative 2x. Right? Can I say x greater than or equal to 0. That is the key. I can say greater than 0, 2x. But at equal to 0, can it be equal to 2 times x? Let me repeat that. When x equals 0, is the derivative equal to 2 times x? Yeah, when x equals 0, 2 times x is 2 times 0, which is 0. Did we find that the derivative is 0 at 0? Yep, we did. Horizontal tangent, we said. So, this is what we have for derivative of x times absolute value of x. Wait. Can I do that? Can I yank the 2 outside and write x if x is greater than or equal to 0 and negative x? Yeah, I can. Wait a minute, this guy looks familiar. What is that? Dang, that's nothing but absolute value of x, man. Yep, you got it. So, ladies and gentlemen, all this time I spent just to show you this stupid little thing called ddx of x times the absolute value of x is 2 times absolute value of x, believe it or not. Once we do that, then piece of cake. Square, ooh, I spoke too soon. I spoke too soon, jeez. Okay. We want to figure out what square root of absolute value of y is in this case. What is y? X times the absolute value of x. I know this. I wish I could draw bigger bars for the outer one, but you're supposed to look at this as absolute value of what? The inside stuff is x times the absolute value of x. What's the square root of this? Well, what is x times absolute value of x? Here we have is equal to x squared if x greater than or equal to 0. Cool, first do that then. What is absolute value of positive x squared? X squared itself. What is absolute value of negative x squared? What? Absolute value of negative x squared? Yeah, what is that? Is negative x squared guaranteed to be negative? Let me ask you that again. Is negative x squared guaranteed to be negative? Yes, because x squared, no matter whether what x is, positive or negative, x squared is always positive. So negative x squared is always negative. So absolute value of negative x squared would be negative of the quantity. What is the quantity? Negative x squared. So negative of negative x squared. In other words, that's x squared. Square root of x squared. So we have, the whole point is, whether x is greater than or equal to 0 or x less than 0, absolute value of x times the absolute value of x is just x squared. So we are taking square root of x squared. What is square root of x squared? Don't make a mistake now. What is square root of x squared? Don't tell me plus or minus 6, man. No, man. Don't tell me x. Absolute value of x. So guess what? This is square root of x squared, regardless of what x is, positive or negative. And that in turn is equal to this absolute value of x. So, thus, what do we have? Y prime. Y prime is nothing but the ddx of x times the absolute value of x. We got it 2x, 2 times the absolute value of x. On the right hand side, we showed 2 times. All of this turns out to be absolute value of x. So 2 times absolute value of x. 2 times absolute value is equal to 2 times absolute value of x. What happened more? Oh lordy. I should have split this into two parts. Maybe after I get done recording, I'll do this. I like this one. Can you believe that? Can you actually differentiate this right-hand side? That looks scary, doesn't it? Yeah, but if you recall the fundamental theorem of calculus, fundamental theorem of calculus says d dx of integral g of x to h of x of f of t dt is f of that h of x times h prime of x minus f of g of x times g prime of x. Cool? F of h of x times h prime of x minus f of g of x times g prime of x. That's what d dx of this integral turns out to be. Let me give an example. Can I ask you, hey, boys and girls, what's d dx of integral x squared to oopsie? What did you do? What is this? Does that look like our fundamental theorem of calculus could be applied? Yeah. What is f of t? F of t is sine t. What is h of x? E to the x. What is g of x? X squared. So if f of t is sine t, f of t is sine t, f of 7 is sine 7, f of p is sine p, f of h of x is sine of h of x, right? What is h of x? E to the x. What is f of h of x? Sine of e to the x. Then what are we supposed to do? Multiply that by h prime of x, that is the derivative of e to the x, which is e to the x. So what do we have as the first term? This corresponding to the f of h of x times h prime of x. We have sine of e to the x times e to the x, derivative of e to the x, which is e to the x, minus sine of x squared times the derivative of x squared, which is 2x. Cool? That's the idea. You must know this. If you know this, then it's rather easy to work on this integral. So let's do the derivative of that integral. Does this look like d dx of integral g of x to h of x f of t dt? Yeah. What is f of t dt? F of t rather, e to the t square. What is h of x? X. So f of h of x is e to the x square times the derivative of x itself, h of x itself, which is 1. So we end up with e to the x square times 1 minus e to the 0, which is 1, times the derivative of 0, which is 0. So guess what? That whole thing is just simply stupid thing is just e to the x square. How fascinating. I need to mention one more thing. Why'd you do that, man? Why can't you just simply integrate e to the t square and then plug the limits and take the derivative? Great idea. Right? Let me repeat that. Why do we have to go through all of this stupid fundamental theorem of calculus and all that nonsense? Couldn't we just simply say integrate e to the t square and then plug the limit 0 to x, and we'll get some expression. Take the derivative of it at that time. Yep. But there is a problem. What? You cannot integrate e to the t square. What? Yeah. Try as much as you want. You cannot integrate e to the t square like a regular thing. I mean, of course, if you write the Taylor series expansion of it and all that stuff, fancy thing. I'm not talking about fancy thing, just a regular closed form solution. No, there is no such thing. That's the problem. Then why is there a function like e to the t square? Who would ever bump into e to the t square, man? Stupid thing. No, don't be so fast. E to the negative x square, for instance. Whoopsie. E to the negative x square is nothing but your bell curve. And anytime you're studying probability, you will bump into bell curves. Any guys, when you take think machine design one, you will bump into distribution, normal distribution, Weibull distribution, and all these kinds of things. You will need that because you'll be studying things like, let's say, some machining shop machines rings of diameter 1 inch. When you machine something to 1 inch diameter, you won't get 1.00000 inches. You'll get plus or minus some tolerance. So there you would be asking questions like, if I have made 1,000 rings, and if I randomly pick 10 of them, what's the probability that of all the 10 falling within the spec? And you will see that many of them will have a nice round figure of 1 inch diameter, and some will be far away from that, indicated by this right side tail, like 1.1, 1.2, and you have to reject that, or the diameter is too small, 0.9, 0.95, something like that, and you have to reject that. But there will be fewer of them on these what are called outliers. So you want to find probability of these rings anywhere from say 0.98 to 1.02. Then you have to find the area under the curve. What is the area under the curve? Integral. You need to find integral of e to the negative z squared dz. So that's not a stupid integral that you never bump into. It's a very practical integral. Cool? All right. So once we know that, we got this, and so we need to look at this as a product, e to the negative x squared times some function of x. So the derivative would be the first function times the derivative of the second function, that's the derivative of the integral, which we just found out to be e to the x squared, plus the whole integral stuff, second function, times the derivative of e to the negative x squared, which is e to the negative x squared, times the derivative of negative x squared itself, which is negative 2x, plus c1 e to the negative x squared times the derivative of negative x squared is negative 2x. Cool. And now if you notice this thing, e to the negative x squared times e to the x squared. If I said that's equal to 1, would you agree with that? There are two ways of showing that. Can I write e to the negative x squared as 1 over e to the x squared? So would we have 1 over e to the x squared times e to the x squared? Isn't that equal to 1? Yes. So this product is just 1. And now, from this big long term, second term, and the third term, can I factor out a negative 2x? Yep, then I do. Would I have e to the negative x squared times this integral, e to the negative x squared times the integral, is that the same as this guy? Cool. Plus c1 e to the negative x squared. Is that the same as this guy? So isn't that just y, this plus this? That's what I did. I replaced the factored out minus 2x and the rest of it with a y. So y prime is equal to 1 minus 2xy. If you add 2xy to both sides, you get back the differential equation. Or you can say the left hand side is this, and that's nothing but 1 minus 2xy plus 2xy equals 1 equals right hand side. See that? What I did is I took this y prime equals 1 minus 2xy and substituted for this y prime. So I have 1 minus 2xy plus 2xy, and these two add up to 0 and get 1. Cool? Gee. Oh, okay, got it. Y prime, y double prime plus y equals tangent x. Is this what? Y double prime? Yeah, we could have a second order differential equation. Well, in that case, all you need to do is simply differentiate twice. So let's take this guy and differentiate. Do you agree we need to apply product rule? Negative cosine x, y prime is negative cosine x, the first function, times the derivative of natural log of secant x plus tangent is 1 over secant x plus tangent x times the derivative of secant x plus tangent x itself, which is secant x tangent x plus secant square x, plus the second function times the derivative of negative cosine x is positive sine x. Cool? And I'm sure you agree with me. This first term is equal to just negative 1, right? Is equal to what? Obviously, man, come on. Can't you see? All this thing is just equal to negative 1. Obviously. You've got to be kidding me, man. Wait. Can I factor out a secant x out of these two terms? What would I be left with if I factored out a secant x? Would I have a tangent x plus secant x? Is that the same thing in the denominator? Tangent x plus secant x? Of course, written the other way. So wouldn't they cancel out? Wouldn't I be left with secant x? So we have a negative cosine x times secant x. Now, aren't they reciprocals of each other, cosine x and secant x? So when you multiply them, wouldn't you get 1 with a negative in front? That's why I said that's negative 1. Cool. Plus sine x times natural log of secant x plus tangent x. What? That is so strange. What is so strange? The derivative of, let's focus on just the derivative of natural log of secant x plus tangent x. That just simply reduces to secant x. Isn't that weird? No, it's not weird. What is the integral of secant x? You remember from Cal 2? Integral of secant x is actually natural log of secant x plus tangent x. So is it any surprise that the derivative of natural log is secant x? Think about it. Let me repeat that. In Cal 2, we learned that integral of secant x is natural log of secant x plus tangent x, of course with an absolute value. So, is it any surprise that the derivative of natural log of secant x plus tangent is secant x? No, it's not a surprise. That's the result you should expect. Cool? Now, if you do that, a second derivative is easy to find. The derivative of -1 is 0. Sine x times, again, the derivative natural log of secant x plus tangent x. We don't have to do all of this stuff. They'll simply say that must be just secant x, the derivative of that. That's what I did. Sine x times secant x plus second function times the derivative of the first function gives you this. Sine x times secant x. What is that? Secant x is 1 over cosine x. So sine x over cosine x. That's nothing but tangent x. So we can write like that. Now we are ready to plug. Left hand side is y double prime plus y. If you plug all of this, you will notice that second and the third terms will add up to 0, leaving us with just a tangent x. That's what we have on the right hand side. And you are responsible for 1 through 37 in exercise 1.1. Wonderful section. There are so many wonderfully interesting problems. Okay? All right, folks.